So, good morning to all. Welcome and thank you for attending the webinar of the FreShER project. I'm Miguel Vicente from WAVEC, and I'm here with my colleague Janette Gonçalves. All the partners of the FreShER project will participate also in this webinar. FreShER is funded by the European Maritime and Fishery Fund, a program from the European Commission. Next. So just a very brief introduction to the project. The full title is Floating Solar Energy Moorings, Innovative Mooring Solutions for Floating Solar Energy. And the main goals of the project are the following: to demonstrate an innovative mooring solution in a full-scale photovoltaic park, which is 50% more cost-effective compared with conventional solutions. Also to make floating solar PV parks more sustainable with easy manufacturing and installation, and with lower transport and maintenance needs. Also, we wanted to increase the knowledge on the system motions and loads and many other aspects of the project, and hence reducing risk in planning and executing future projects, including near-shore deployments. Also, as a consequence of all these developments, a contribution to the definition of standards in the sector of floating solar. The project's FreShER is close to its end, and the 5 megawatt park was inaugurated last July in Alqueva Dam in Portugal. So introducing the consortium partners, the partners from the consortium. There's EDP with two groups, the EDP Generation and EDP, the Center for New Energy Technologies. EDP is the Portuguese utility and is responsible for the whole global project, which will be mentioned later today. From these partners, we will have Pedro Albuquerque and Tiago Lourenço participating. We also have Hybridization from Spain, a company dedicated to floating technologies and design, and they were the developers of the floats and the pontoons. Also, the Research Institute from Sweden, they were responsible for the laboratorial validation and loads monitoring. Puya and Ermina will participate in the webinar. There's CFlex, also from Sweden. It's the partner coordinator of the project. They are the providers of the elastic mooring solutions with the progressive dampening. And finally, WAVEC from Portugal. We developed a numerical model to estimate the platform motions and mooring loads. There's a website of the project where you can find some information. Sorry, and it will be updated soon with the most recent results. So today we will have the participation of Mr. Ignacio Asenjo, policy officer from the European Commission, and then following that we will have all the partners covering the several topics of the project. And finally, we will have a Q&A session, 15-minute session. And next. So we would like to thank Mr. Ignacio Asenjo for participating in for accepting the invitation to participate in our event. Mr. Ignacio is a policy officer in the Directorate General of Energy from the European Commission. He's an international relations expert and political scientist, and is responsible for the solar energy strategy from the European Union. Mr. Ignacio, please, thank you very much. Welcome, and let us know your view on the solar energy sector. Please, the floor is yours. Oh, okay, so Mr. Ignacio is not here right now.
No.
So maybe we should proceed, and then
yeah, let's proceed, and
yes,
then we
exactly.
can make a little void when he gets back, because he was here
yeah,
recently.
Okay, let me, before passing the word, giving the word to Pedro from EDP, let me say that the audience can pose some questions using the Q&A icon. Okay, so Pedro, please lead the presentation now. Thank you.
Thank you, Miguel. Good morning, everyone. I would like to start presenting you Alto Rabagão. Alto Rabagão was a small pilot project that was developed in 2015. Next, please. And it was the first floating platform with PV panels in Portugal. We have 218 watt peak of power, thanks to the 840 modules of 260 watt peak each. This park is directly connected to the dam, and it was what made this project even more special and challenging at the time, this fact of being placed near the dam, because of this variation of the water level that needed to be took into account in the mooring system design. And for that, we had the huge contribution of CFlex that developed a solution based in 8 mooring line system with 6 CFlex units with V connections to the bars. Next, please. And basically, this project is being kind of a box full of surprises since the opening in 2016. And it matches with our intention of learning, of improving. It was a pioneer project, and everything were new for everyone. We had a lot of unexpected situations that acted as an improvement opportunities for future projects, since things like float years broken, creation of waving effect based on the elongation of years, problems with the low buoyancy of floats, and mooring lines twisted. All of these basically compose the challenge for this FreShER project. Next, please. And now we have Alqueva. Alqueva is the second one, the first licensed hybridization project in Portugal, with the intention to demonstrate here the complementarity between different sources of renewable energy. We have hydro, 2 generators with 143 MVA, and the PV. And the storage, we have pump and the battery with 1 megawatt and 2 megawatt hour of capacity. Basically, here we have developed the 5 megawatt platform with a total area of 4 hectares, composed by more than 11,000 PV modules, distributed by 23 string inverters, connected here to a 15 kilovolt floating substation. And this is integrated in the auxiliary services of Alqueva 2, and then connected to the transmission network. Next, please. Okay, and basically FreShER is part of this big hybridization project inserted here in package 2 and the chapter of mooring and anchoring part. Okay, now the presentation will proceed with Miguel Redon that will detail a little bit more about this FreShER project. Thank you.
Sorry, Miguel Redon, just to check if Mr. Ignacio is here, but I don't think so. Well,
I think he's struggling with his connection because I saw him recently.
Yes. Okay, so let's move on.
I'm here, and the
okay.
connection is okay. I'm sorry.
Okay.
Lost the connection indeed.
Okay. So you are sharing,
There.
you will be sharing a presentation, right?
So I make my presentation now. I'm sorry because I was out, so I didn't know
Yeah.
what was
Okay.
happening. That's right. Should I
Yes.
go?
Yeah, yeah,
Okay,
yeah.
very good.
Thank you.
Thanks so much for this invitation. It's a pleasure to be here representing the European Commission. I work in DG Energy. Sorry, because I have a now. I work in DG Energy, and no, I need to. I'm sorry because I made a double connection. I really need to. That's right. I'm sorry. Now I'm starting really. This is my presentation. I work for the European Commission, Director General for Energy. I work in the unit in charge of renewables, and I'm more specifically working on the solar sector. I will make a presentation that will provide a general overview of the European Commission policies regarding solar energy. And then I will zoom in specifically on the topic of what we call innovative forms of deployment, including in particular floating PV, which is the subject of the conference today, and your specialization as researchers and companies. But I think it's important for you to have a general policy framework regarding solar energy, because whatever affects solar energy policies in the European Union will affect, in particular, floating PV as well. So here it is. The European Union Solar Energy Strategy was adopted in May last year as part of the package that we called Repower EU package. And it summarizes the policies towards solar energy and also sets the directions for the future policies to come. So we have analyzed a set of challenges for solar energy and how to address them. First of all, as general framework, we need to talk about the general Repower EU, and I think it's important to talk about this general framework because what we are seeing today with recent decisions by Russia is that this framework is not going to change for the better in the next few months, that we are entering a sort of new normal. And it is very clear that the prices for fossil fuels are not going to stabilize in the short term. So we need to continue this policy for the future. Our objective is to achieve independence from Russian fossil fuels. As you probably know, we don't import Russian oil or coal any longer, and now Russia represents only 9% of imports of natural gas from more than 40% before the war. We are importing already more LNG, liquefied natural gas. We are importing more pipeline gas from Norway, from Algeria, and from Azerbaijan, for instance. We are increasing our biomethane production. We are saving energy. We are making push on rooftop solar, on heat pumps, and accelerating the deployment of wind and solar to accompany all this. So the double idea is to diversify our gas imports, to reduce our dependence on fossil fuels by accelerating our transition to renewables. We want to increase the target for renewables from the 40% that we propose in 2021 as part of the Fit for 55 package to 45% by 2030. The target of 20% by 2020 was achieved with a total of 22%. So we have ambitious targets, but we know now that they are achievable. Specifically about the EU solar energy strategy, here are the challenges we have identified. First of all, we in a Repower EU scenario, so in a scenario where we really manage to reduce our dependence on Russian fossil fuels, plus all the objectives that we already had for carbon neutrality by 2050 and reduction of 55% of carbon emissions by 2030. In all that complex scenario, we predict and we have set ourselves as target to achieve 600 gigawatt of installations of solar energy, solar PV specifically in this case, by 2030, compared to 136 gigawatt in 2020. These are figures in alternate current, so they don't really correspond to figures normally provided by the industry, although they are not that different in the end when you look at it. So that means that we have to multiply over the current decade our capacity installed of solar PV by more than 4. So we need to accelerate the expansion. And to accelerate the expansion, we need large-scale deployment, so utility-scale deployment of PV and of wind, of course, based mostly on auctions for renewables, on market signals, on long-term markets that need to be further developed through, in particular, power purchase agreements, and also through new forms of state subsidies, such as contracts for difference, two-way contracts for difference that are becoming sort of the new norm in this sector. We are also accelerating rooftop deployment, decentralized rooftop deployment that is really taken off now in most European Union member states, which is linked to self-consumption. This is a very important aspect to us. But we also think, and I think this is the key for this context, the context of this conference, we need to push innovative forms of deployment. So we can't rely simply and only on utility scale and decentralized rooftop deployment, which is the case today mostly. We need to pay attention to other new forms of deployment, including, of course, floating PV, and I will develop this a bit later. We have also identified and addressed two horizontal challenges for renewables deployment and the acceleration of the expansion, which are permitting procedures, big problem in most of European Union member states for deployment of renewables, a #1 problem in a way, and then also to address bottlenecks in the skilled workforce, in particular for the deployment itself, for the installation, and in particular in rooftop deployment. Just to underline that rooftop deployment is very important for us because it provides, if we provide citizens with the right incentives, it can be used to address energy poverty, it can be used to shield citizens from the volatility of fossil fuel prices and transmission to electricity prices. But it is a complex issue that needs to be addressed calmly. And we need to address in particular the issue of self-consumption, in particular collective self-consumption in buildings, in apartment buildings, and energy communities. We also in the solar strategy look at supply. We think supply is a very important aspect, supply of solar PV. We have a clear over-reliance on imports from a single country today. This is something we want to address, and we have the need to establish sustainability requirements for PV systems sold in the EU. To address all these issues, we have issued 4 flagship initiatives that I will not detail in this context. Those are the EU Solar PV Industry Alliance. This is a way to address the supply challenge, the permitting package with new legislative proposals and also a recommendation and the guidance to member states on how to improve, lighten, speed up permitting procedures, the EU Solar Rooftop Initiative to accelerate the deployment of solar PV in rooftops, the EU Large-Scale Skills Partnership, which will cover renewables in general, except offshore renewables, which are already covered by another skills partnership. And finally, apart from these 4 flagship initiatives, a guidance to member states on innovative deployment, which I think can be of interest here. As I said, I won't go in detail into our skills initiative. We think skills is a very important challenge. We are seeing bottlenecks, very serious bottlenecks today, since, as you probably know, the expansion and deployment of solar PV is already accelerating. We are probably reaching 39 gigawatt of installations according to the industry this year, which is a tremendous increase compared to last year of 27, which was already a record year. And we are seeing bottlenecks in terms of number of companies that can make those installations and also the available skills for those installations. So we as European Union want to support the sector in that regard. The EU Solar PV Industry Alliance is simply a way to put together all relevant actors in the manufacturing and the whole value chain of solar PV in the European Union to try to ensure that some innovative projects for next generation technologies can actually brought to fruition, and we can manufacture more of those components in the European Union itself to reduce our current dependence on imports from a single country. And this has to be combined with diversification of imports from more countries as well. And these also will include a research and innovation pillar that still needs to be developed. This alliance will be launched by the end of the year, in principle. At least that's what we hope, and I think we will reach that target. Rooftop initiative, I won't go into detail on the rooftop initiative. I know this is not the right audience, but we think it's a very, very important aspect of what we need to achieve to facilitate self-consumption, energy communities, and the deployment of rooftop solar PV, which encounters undue obstacles in many of the EU member states. Finally, we have taken the commitment to issue a guidance for member states to promote the development of innovative forms of solar energy deployment. Was mentioned before, we call innovative forms of solar energy deployment anything that is not the current model of utility scale deployment, ground mounted, and rooftop PV. We have chosen these 5 forms as the most promising and prominent, and the guidance will be based on a study that we are contracting right now, and we have the results in about a year, to identify, first of all, where are the regulatory and practical and even industrial barriers that some of these forms of deployment are encountering today. And also, where are the best practices in some member states that what we can try to replicate elsewhere. It is just a guidance. It will not be legislation. Will not be forcing member states to do A or B, but we will bring them the knowledge about where the barriers are, and in their own member states, and in their own legislation and their own regulatory environment, where the barriers are, and how to address them. These barriers are often linked to the fact that innovative forms of deployment of solar energy mix different activities always. And so they make energy production products and energy production activities in a framework or even integrated in a product that has been made for another purpose. And that often leads to the mix of 2 different forms of regulation. That is very clear in the case of hybrid PV, where you use the same land for agriculture and for energy production, and that can sometimes clash with regulations, with subsidy systems, etc. The same for transport infrastructure PV, or actually other kinds of infrastructure. So now we tend to call it infrastructure integrated PV. So it's not only transport, but it can be other kind of infrastructure as well, where you have in particular rules related to safety and to land that has to be left empty and cannot be used for other things. Can we use that land for PV deployment? Vehicle integrated PV, there are similar problems when it comes to the regulation of how vehicles, how cars in particular are being manufactured, designed and manufactured in the EU. How can we integrate PV into that system? And building integrated solar PV in particular, it can be thermal as well, but it's mostly building, also knows these kind of areas about building, construction regulation, and energy regulation. Floating PV is we have added floating PV as one of these forms of deployment that we consider innovative, be it onshore, so mostly in lakes and dam lakes, or offshore. We think we still need some research to actually make it fully commercial floating PV, and we want to check whether there are regulatory challenges or even industrial challenges that we can help to address, and where we can find good practices. It seems from what we know from the sector and what we have heard already in this conference, that Portugal could be one of those models to follow, a country that is developing good practices in this sector. So this was my presentation of the general framework, the general policy framework for solar energy, for innovative deployment, and specifically for floating PV. This is what we are trying to do from the European Commission. We are looking carefully at what is happening in the sector, and we hope to help in the future, because our opinion in the European Commission is that we need all possible forms of deployment of solar energy, because we need, as I was saying in the beginning, 600 gigawatt by 2030. So any form of deployment is welcome, as long as, of course, other regulations and other demands are also covered, in particular on the environmental side, and of course on the acceptance by local populations. So from the European Commission, we are working to try to facilitate all forms of solar deployment, including, of course, floating PV. Thanks a lot for your patience and for your time.
Thank you very much, Mr. Ignacio Asenjo, for sharing your views and the solar energy strategy, and to show the commitments from the European Commission on renewable energies in general, and in particular in solar energy, which is, as I believe everybody understands, is of the utmost importance at the times we are living now. Thank you so much. We will resume the presentation. So Miguel Redon, if you can take the floor now. Thank you.
Okay, thank you. Next, please. Basically, the first challenge is that all the team has to cope with, basically, are due the site where the installation were going to be installed, and above all, the solar production issues of what is the net, installation scheme, and so on. The hydraulics of the dam also spot or pay our attention at the beginning. Next, please. There were studies about the hydraulic simulation and the peak discharge of the dam, with water velocity vectors around 1 meter per second, and bathymetry studies to see or to check the bottom of the dam, basically. Next, please. This suggested or give rise to a difficult bathymetry with bottom situation of and water depth from 50 to 75 meters, and maximum water level variations of 20 or 23 for minimum water level. Next, please. This, together with other studies of waves and wind, basically suggested or give rise to all the environmental studies and the characterization of the loads of this project. Basically, we have a demanding situation of wave, like you can see with the fetch, the significant wave height, and the peak wave height, and also corresponding to the wind. There was a lot of studies and other research that we'll talk about in the presentation, but basically also we started from a fundamental wind speed of 30 meters per second and a characteristic wind value, or basically the design value for all the project of 38 meters per second. So from that and a water current of 1 meter per second, we started what it will be the design of the different schemes of mooring that all the partners studied at that moment. Next, please. The assessment of the different mooring solutions started, next, please, with a brainstorming of different situations where we wanted to think out of the box, or basically it's not out of the box, but think new solutions in order to cope with the challenges and with the aim and scope of this FreShER project and the challenging objectives of the project. We have here in this slide the different schemes that we started to study with pros and cons, not only in terms of engineering challenges, marine and hydrodynamic challenges, but also from the point of view of the solar installation and its power production. From that, next, please. Next, from that, we think or we pay attention in two specific options where we made an insight design of both of them. One option, the first option, it will be a continuous external pontoon, which receives all the mooring lines. And from that, the characteristics of the plant and some advantages or disadvantages of this situation basically give us some pros and cons of higher power capacity, how it was the implantation of the area, the load distribution, and mainly the disadvantage of this situation was the number of mooring components and the higher cost of it. From that, also we studied option 2. Next, please. That it will be a discontinuous pontoon with a lower number of anchoring, of higher capacity, that this also had some troubles in terms of where you can situate or accommodate them in the bottom of the anchoring because of this challenging profile of the bottom with a very, very steepy sides and not really flat areas to situate or accommodate in a comfy way all the anchoring. And basically, the situation could have a hydrodynamic advantages to accommodate the movement and so on, but it was very, very bad, or the main disadvantage is that due to the space, the footprint of the plant in terms of the permits to accommodate the plant, the power production of the plant was significantly reduced, because at the end you have a less potential area to accommodate the PV panels. Next, please. With that, we develop mostly both situations or both options in terms of all the environmental loads, hydrodynamics of the plants, and so on, but with mainly focus in this option 1, with which was the base to the upfront engineering design that was submitted to the authorities in Portugal, and you will see more in depth the outcomes of these approaches in the following slides. Next, please.
Okay, so there was a need to analyze and estimate platforms' motions and mooring loads under extreme environmental loads conditions. So a time domain model was developed, taking into account the most relevant dynamics, and in particular, counting with the combined action of the polyester ropes and the C-flex units, which has a highly nonlinear behavior. This model has inputs the geometry of the platform, a simplified version of the geometry, the environmental loads from wind, waves, and current, the bathymetry, the properties of the moorings, and also other dynamic coefficients that are computed with wave-linear theory. And the outcomes of this model are the motion displacements, the platform displacements, and the mooring lines elongations and loads. We're not showing here the numbers, but the preliminary results show that the motion of the platform was within the allowed range, and also that the mooring loads were also within the limits of the C-flex unit properties. Next, please, and Pedro.
Okay, thank you. Okay, regarding the licensing process, our Portuguese Environmental Authority requested to TULNEC, that is our civil engineering National Laboratory the analysis of the mooring project, and then we have received in December 2019 the first analysis report with some recommendations, namely based on the importance of following the Eurocodes, the assessment of the nonlinear and dynamic behavior of the platform, the determination of wind actions with different configurations of modules in the wind tunnel, and the usage of deterministic modules of wave generation and propagation. Special aspects like the berthing of vessels and the impact between platforms, impact of other floating objects, breaking of mooring lines, anchorage or other connections were also took into account. Also, and considering that we are talking about a dam, the risk of obstruction of the surface spillways and of jamming the floodgates with floating materials and panels were also analyzed. Next, please. Okay, and this led to our front-end engineering design, replying to NEC demands and recommendations, where FreShER have participated. Also, and due to the lack of standardization for floating PV, EDP, EasyEngineer, and CFlex were invited here by DNV to participate on a GIP to develop the first best recommended practices for floating PV based on this engineering document that we have made before. Next.
I follow now. Basically, the material or the fundamental, one of the fundamental studies that give rise to the FIT in front engineering studies from LENEC, and also that I think that is one of the first times that some partners of different schemes, floating, hydrodynamics, final supplier, IDP, and so on, work together and we look into the wind action and the different ways or different approaches that could be assessed in order to get a better approximation for the loads in a floating solar plant. Basically, we look into the Eurocodes, the British and Australian standards more devoted to maritime environments, thanks to CFlex support, and also computational models and wind tunnel test. Basically, from that, next, please. From that, also we pay attention to different position of placement of the PV panels, not facing to the south, but turning them and looking for an east-west installation where we have a significant reduction of loads, which mainly the mooring lines we will reduce the capacity and the number, and in terms of the generation, it could be compensated by the reduction of the mooring cost. Next, please. In this stage, we made one of the main decisions of the project that it was to change from or to look into from a change in the disposition of the mooring lines, not in a perpendicular way, but thinking in a diagonal or 45 degrees position in order to cope with the forces with less number of mooring lines, and thanks to our ability or the chance that this continuous pontoon could have. Or at the end, the mooring lines were not going to reach the floats, a single float with lower capacity of the plastic, but we were thinking in a more robust structure or superstructure that it was these continuous pontoons that help to make a design more closer to what it will be a pontoon scheme. Next, please. This for sure was supported in different studies. The basic wind simulation from the south disposition that they were at the beginning from the east to west with different CFI models. Next, please, to confirm that basically mainly the drag coefficients and the lift coefficients of the plant suffer or were significantly reduced, which at the end, with the demanding peak wind design of the plant of almost 40 meters per second, could also have an impact on the total wind loss of the plant. Next, please. This table summarizes what it will be the approaches of the wind calculation from different models, from more Eurocode or traditional approaches to maritime environments and CFD and wind tunnel test, and with different wind profiles to reach what it will be the east-west configuration that at the end the team and the partners took as a wind load of the plant. Next, please.
Okay, and we move from the design phase into the actual implementation of what we are going to install from this. This is looking at the actual installation layout for the mooring lines. So there were basically 20 anchors and 20 primary C-flex mooring lines connected to the continuous pontoon, which is on the perimeter and circumscribes the platform for the solar panels. Each main C-flex of the 20 lines is split into 4 more lines. So that means there's 80 attachment points to the continuous pontoon. Next. You can see from the decision to separate the corners of the pontoons in this picture here, this gives the ability to have more flexible, less rigid continuous pontoon around the floating solar platform, because not all of the time the wind will come from directly one side, being either a true north or a true west or true east side. It can come from a northwest or a north-northwest, and also change directions within a storm. So this gives the platform the ability to move better with different wind directions, and make it so that there's more even spread of loads no matter which side the wind is coming from. Next. As you can see here, there's a lot of crossings of mooring lines since we have four attachments connected to one C-flex line, and on the other side, 4 attachments connected to one C-flex line. This is not a great representation in a 2D view, but if we were to look at this from a 3-dimensional view, we could see that the mooring lines are not touching each other in most cases. There are different scopes for these mooring lines. So for example, MCN3 is going to be above MCN2, so that when the platform is in a high water level, let's say, those lines will be a little bit closer to each other. And if some of the upper lines happen to be in a touching position, that's when we have the chafe guards that are placed over the ropes for the potential touching lines, so that will not degrade the ropes during function. But other instances where there's a low water level or medium water level, the lines can be more spaced out. So this has been taken into account for all the surrounding mooring lines in these situations. Next, please. To look at the multi-connector interaction with the primary pontoons, the attachment points were placed in such a way for these top lines that it was an even distribution of load throughout the primary pontoons here. So it was devised to put them at these joint locations, and that would allow for a good distribution among these platforms themselves, so that the pontoons were not pushed and pulled in odd directions. They were all done in an even fashion from the mooring lines. So we go to next. If we start at what the actual mooring line looks like from the bottom anchor, the majority of the mooring line is actually composed of the bottom mooring line rope. Some of these depths, as stated earlier, were up to 70 meters deep. So this bottom line rope that reaches from the anchor to almost the surface of the water in some locations is quite long. It really makes up one of the majority length of the distance of this mooring line. Next. The next unit from the bottom rope goes to the C-flex unit. The C-flex units were different lengths based on the different scopes of the mooring lines around the platform. So some C-flex units needed to be around 11 meters of unstretched length, while others needed to be 18 meters of unstretched length. And these lengths at full strength, full stretch would have gone from 20 to 30 meters roughly. when they're stretched out completely to high water level. Next. The top attachment point from the C-Flex unit to the top ropes is the new multi-connector unit, which does an even distribution spread of 2 lengths of ropes, continuous lengths of ropes to the top mooring lines that attach to the pontoon. This does provide for the even distribution and is one of our very important innovations from the FreShER project. Next. And you can see here, it's going to go down under the water. Here is a virtual reality representation of what a taut elastic mooring line looks like. This is not the exact configuration that was used in the FPV project here, but it gives you a visualization of what a taut mooring line looks like with water level variation moving up and down. As you can see, that the mooring line is never slack, never touches the seabed floor, so it's always under tension, you say. Okay, next. Next. Yeah. Okay, this is the, oh, sorry, please go back. This is the summary of the innovative components that were brought about by the FreShER project. We have a C-Flex unit. This one is being composed of an 8-houser C-Flex unit. Anti-torque device, because the C-Flex units were so long, some of them up to 18 meters and stretching up to 30 meters in length, there needed to be an anti-torque device to keep the units straight so that they were working properly. There's a tension measurement device, which was used when there are depths of such as 70 meters deep. We needed to have a system to measure the tension on the unit for accuracy and have that be able to be done from the surface. So that's an O&M innovation that was created especially for this. And also the W configuration for the top mooring lines facilitated by the multi-connector. Next.
To follow, in terms of the external pontoon or the element that is going to receive these multi-connectors and the different legs of the main mooring lines, the main diagonal mooring lines, the plant is going to have 4 perimeter floating dikes. The characteristics, or the main characteristics of the dikes is that have a length greater than 10 meters and a width of around 1.5, and the displacement of buoyancy is over 5 tons. Each dike is composed by a structural element, a pontoon, link between each of them with an elastomeric joint connection that you will see afterwards. Each dike, as I told, is linked to the floating plant, also with an elastoplastic joint, also developed in this project by FreShER. And in summary, the mooring system, which ensure the station keeping of the floating solar plant, is connected to this perimetral dike. Next, please. The external pontoon is made of ultra-high performance concrete and is an element totally designed by FreShER together with a preferred concrete, ultra-high concrete company. We have the intellectual rights and property of this design just approved in Spain, and with the rights now for Europe and rest of the world. Basically, the challenges and the benefits of the material: it has high durability, high strength, and lightness in comparison with it will be the normal concrete material. And the pontoons are filled with polystyrene. Next, please. Not only we have to have a robust pontoon of ultra-high performance concrete, but also the connections between the different sections of the pontoon has to have the capability to receive axial, flexural, and rotational capacity. And this not only in terms of forces, but also to receive what it will be the main mooring lines points of the C-Flex lines. Next, please. This provoke or this has an in-depth structural studies of the material, the sections, in terms of the capacity to resist the different forces in ultimate limit states and serviceability limit states. Next, please. And the hydroelastic approach in terms of the floating array dynamics of the plant with the dikes, the connection of the dikes, and the connections between the dikes and the floats, the plastic floats with special elastomeric materials. Next, please. This also provoke the distribution of forces, how all the elements could cope with the different combination of loads, wind, waves, and currents with the combinations of the Eurocode, or basically the combination of ultimate limit states. Next, please. And basically, in summary, the external pontoon in terms of also a progress in what it will be the design of floating solar installations, we believe that provide us robustness of the design to cope with challenges in terms of safety, reduce of mooring lines, or increase the capacity, the force capacity of each point, and also to have a ring or to have an element from where a lot of activities, not only in installation stage, but also in operation, workers can pass through, you can pass the cables and so on with high buoyancy and high capacity. For that, I think that is not only a movement from what it will be the Marina scheme of pontoons design, but to fit into the challenging and cost-reducing cost of floating solar and in terms of renewable energy, I think that this solution brings us benefits in terms of industrialization, flexibility of design to have different points of connection as we want, or each plant will be different, speed of production for sure, and high performance and availability. Next, please. Sorry,
I think
you're
muted, Puya.
Apparently you're not muted, but we cannot hear you.
Yeah. Now Puya, a researcher from Rice Institute, was going to take this section of all the monitoring and studies developed through the project.
Let's wait just a little bit more if we can enter. Maybe we
Lars,
move on,
maybe,
and then if
Maybe-
we is able to.
Lars, you can
maybe
take the first ones, and the other ones you take it time you want, and that's all.
Maybe I can, if you back
Okay.
one slide there, I can take this presentation. Oh, Puyo, are you here now, or?
Do you hear me now? Or?
Yes.
Yeah.
Yeah,
yes.
now we can
Okay.
hear you. Okay.
Okay, sorry for that.
No problem.
Yeah, so I'm explaining monitoring solutions for the load, how we place different kind of sensors. And so the number one, the orange one, you'll see the tools which are placed between the seat and close
Actually, we are.
Now we need
You're-
to switch over.
Pontoon. So there are 8 of them.
Your connection is not good, Puya.
Puya,
which are
Puya.
top lines.
No, sorry for that.
Okay,
So
sorry for that. Yeah.
yeah, so your connection isn't working. Unfortunately we need to move over this, and maybe I can explain a little bit more because Puya's connection isn't good enough for this. So what Rice has been doing is the monitorization and putting these load cells on the system, both of course on the top lines here. There's the traditional load cells, but there has been also development of very specific load load cells on the connection points on the Isinere system and between the Isinere system and Isinere outer pontoon system. So these are very highly specific connection points here. So I think we can go to the next slide. And this is the coupler unit, the logger base that is of course based on the platform that is now connecting all these logger sites and these load cells to the loggers, and which we can then monitorize these loading and compare them to the theoretical calculation loadings that we have been doing during the setup of this project. So this is going to be extremely important for us for a validation, and one of the few systems in the world that will be able to validate these loads. Next. This is an example over a laboratorial validation of the multi-connector, where I think, yeah, there is a next slide as well. You see here how this is actually video. Yeah, you see how this was pulled over many times, more than 100,000 times. So you will see a small movement in the tension or the components here to check physically about long-term abrasion and long-term chafing in the system. So there has of course been these kind of systems, and besides the FMEA perspective on looking at these components as well. This is one example of the laboratory validations of the multi-connector. Next.
I take them, Lars?
Yes,
Okay.
yes, you can do this.
Also in terms of the design of the pontoon, basically the main testing was focused in the quality of the material and the daily test of the compression strength of the material, and the bending of the pontoon to a 60% ultimate design load, with measurements of the deflections and microcracking measurements of all the production of pontoons. Also, the different tests were carried out with different proposals for connection between the pontoons to get high capacity and accommodation or rotation of the joints. Next, please. And this was made in the factory, where were made in Perfor factory next to Valencia, with the cranes and the capacity to rotate and to rise the different pontoons, with measurements of the flexural bending in the material, in the pontoons and the connections and the elastomeric connection also. Next.
Okay, now about the anchor's design. It all started with some geotechnical characterization that consisted basically in 4 drilling holes with core extraction, represented here in these 4 head circles. And basically, FreShER has shown that mooring design and anchor design are dependent because of the fact of costs of anchors have an impact of an impact on the mooring selection. Next, please. Okay, we have tested some prototypes of 10 tons with spikes, and 15 tons, basically pull-out tests near the shore, using this specific structure fixed with 2 other anchors to guarantee that it won't move. The objective of these tests was to obtain empirically its drag coefficient, since the test ended when the test anchor started to move. Next, please. Okay, at the end, and for security reasons, we have used anchors of 20 tons with these friction spikes to increase the traction capacity and to give some more security to the whole platform. Next.
Lars?
Yes.
Okay.
So as you all know, we wanted to achieve a big much higher efficiency on the capacity of these mooring systems, and we had needed to do some comparison to something else. So we used the Alto Rabagao and some other older installations to compare to. As you heard about Alto Rabagao mentioned before here, and we're going to continue comparing to that. The C-Flex units in Alto Rabagao were 6 hoses unit with 10-meter lengths, versus in Alqueva, and they were a little bit bigger, 8 hoses units with average length of 15 meter. The lengths, of course, is due to the bigger water level variation that we have had in this situation. The multi-connectors used in Alto Rabagao were the traditional V connections, 2-to-1, whereas in the Alqueva we developed the W connection, which is a 4-to-1 connection. The top ropes in Alto Rabagao were 2 attachment points directly on the spreader bars, whereas in Alqueva, as you've seen, the 4 attachment points goes to the pontoons. Below there, you have the comparison of the design of the systems, where you see a much more robust system, and of course, much bigger. You need to consider also that the larger Alqueva is 21 times larger, of course, than the small Alto Rabagao test facility. Next. Here you got a little bit more numbers. The power generation from Alto Rabagao was a 218 kilowatt peak, whereas it was 4.6 in Alqueva. The water level variation is 30 meters, while you saw the very much longer scopes in Alto Rabagao that we couldn't use in Alqueva because of the distances to the lease lines. The water level here is only 80 meters, still is a lot. The wave pattern is roughly the same. The anchors are roughly the same as well. I think the deepest part of Alqueva is actually deeper than Alto Rabagao. Then the next part of the, sorry. The lower part of the presentation here, or the slide, you see that if we were going to have the same design as the Alto Rabagao design, we would have to use 129 anchor points in Alqueva and 129 mooring lines if it would be the same design. And it would have needed 258 attachment points compared to the 16 in Alto Rabagao. If we would have done the same design, the total capex would have been almost 2 million euros for Alto Rabagao, compared to the 80,000 euros for the test facility. What we ended up with in Alqueva, with the FreShER design results, we ended up with 20 anchors for the platform. The parenthesis shows the 4 anchors to the transformer station. Of course, then 20 mooring lines to the platform and 4 to the transformation station, and 80 points, as was mentioned earlier, in the total cost of only 376,000 euros. So we're going to show, this is of course the capex only. We're going to show you, the next slide is a lot of numbers, but we're going to focus on the first red one, the column 1, which is the Alto Rabagao one. We're not going through all these numbers, but it's extremely interesting to see how these different reiterations in our project has led to a significant cost saving. We have looked through numerous different alternatives, different options that has been described here earlier, and with different alignments of the mooring lines, different directions of the panels. And you will see that, of course, the capex mooring the capex cost of the moorings is very much up and down here. But at the end of the day, we needed to validate and get to the goal of FreShER. And the goal of this development was to lower the LCOE, the levelized cost of energy of the mooring lines, by at least 50%. We have surpassed this overreaching goal of reducing it to 50% by achieving 63% reduction of the cost of the mooring system. And the LCOE of the mooring system alone is 0.039, as you see there, euros per kilowatt hour. Next.
Okay, so as wrap up, and in terms of what was the exploitation of FreShER projects, so we went for 2 workshops, one to kickstart the exploitation efforts, and another one for consolidation. And here we have tried to identify the main innovative concepts from FreShER, also the patents and the utility models that were within the consortium, and finally the key exploitable results and the strategy that should be followed by each one of these PRs. So in terms of innovative concepts, they were already widely described by my colleagues before, but we have identified 8 of them. So the innovative mooring solution for floating PV arrays, the type of pontoons to be used in these floating PV projects, the anti-torque device for mirroring of floating PV systems, and the multi-connector also for the moorings. The simulation of floating PV platforms behavior in water reservoirs, the pontoons connection for floating PV systems, the PV panels orientation, in this case east-west, that was in this way decided for cost reduction, and the load assessment methodology. In line with this, we have 4 patents and utility models in the consortium, so 2 from CFlex and 2 from EasyGener. The first one, the rotation limiting device for progressive elastic device, is the anti-torque device, and the force distribution coupling device is the multi-connector. Then we have also the nestable modular floater for floating solar plants and the PV panel pontoon structure. Next one, please. So, and to conclude this, so we defined 5 key Rs. The first one on the design and site assessment methodology. And as a strategy, we consider that this methodology can be replicated in future commercial and R&D projects, and also as consultancy services that the companies that were involved in this development of this methodology can provide. Then the mooring system, which is IPR protected by CFlex. With the demonstration in this project, we consider that this can be mass produced. And of course, after this mass production, so reducing the costs and applicated in future commercial floating PV projects, and also in other floating sectors. Then the pontoons concept, which is IPR protected by EasyGener. We consider that this can be applicable on future commercial projects. Due to its characteristics, it can be used in more exposed sites for other floating sectors like offshore, enabling also the max production. These pontoons have lower maintenance needs and also low cost maintenance needs. In terms of the mooring system sensor, so we developed a methodology for the validation of the load assessment, the next TR5. RISE is the company responsible for this validation, and we went for a placement methodology of the sensors that enabling also to reduce the costs, and that we consider that can be applied for validation of future R&D projects related with moorings, and also providing consultancy services. Finally, the load assessment. So this methodology already explained can be replicated in future commercial R&D projects and also consultancy services. One important milestone of this project in terms of knowledge transfer is that this methodology was used for some standards creation for floating PV through the NVGL, where some of the partners of the consortium participated on these efforts that were very relevant for sector maturation and to engage possible investors. And that's it regarding the exploitation.
Okay, thank you very much. So we are at the end soon of this presentation and also soon at the end of FreShER. But this isn't going to be the end of it. I mean, this is the beginning of the use of these components and these developments and these results that we've been seeing. We will end the project now in September this year, but it will of course be under demonstration during the next 35 plus years to come. And the outcomes that we've had from FreShER has been significant, and we see that we already are starting to be utilizing these things in other projects globally in upcoming floating PV projects. And there are so many conclusions also from the research that we've been doing in FreShER that will be transferred definitely to upcoming standardization processes that is already on their way. There was actually an inauguration on one of them Monday this week. The achievements of the FreShER project contributed also to the increase of confidence, starting, of course, in the sector of in Portugal, where most of you might know that there was these auctions coming out, and like Ignacio said here earlier, maybe Portugal is the lead country in the Europe definitely, or perhaps even in the world, with pushing forward for floating solar. And of course, FreShER has been a part in that process and has been possibly to give more and increase the confidence for these entities. And the government is now facilitating this auction for the floating projects and many reservoirs across the whole region in Portugal. So I think after that, we can move forward to the Q&A session, right? Thank you very much for listening. And this is a magnificent build then from the installed projects. And we can move over to the Q&A session. We have a couple of questions here. The first person is actually putting two questions in play here. And I think this is directed to C-Flex actually, so maybe me and Charles can reply on this. But one question is, how does the multi-connector ensure an even tension in the 4 connector mooring lines? And this is extremely good question, because this has been an issue in many of the floating solar projects in the past. Maybe you know that there has been some situations in the past where static lines had been breaking and stuff like that. So the even tensioning is extremely important. And maybe Charles, you can also lead that reply a little bit from your experience in this industry to show how this is automatically done through these multi-connectors.
Yes, is very, very interesting with this multi-connector. The way it was built, it only utilizes 2 continuous ropes to attach 4 points on the pontoon. So being that the lines are evenly distributed, because there's only 2 continuous ropes being used, when you need to pull on one particular point, it automatically goes to the other side as well. So when we're doing the installation, when the C-Flex, when the base of the multi-connector is stretched, so when it stretches the C-Flex, that line is tensioned. So then all 4 points can just be connected to the pontoon directly as the C-Flex is tensioned in one spot. So it's actually very easy for the installation to be done quite quickly and very accurately in that matter. So, and also if it needs to be disconnected and reconnected again, it's the same disconnection method to tension from the main unit and remove the lines and do anything that's necessary. For example, if we need to do anything with the sensors, there's some sensors on one of the mooring lines, so that can be worked on independently. So yes, the even distribution of the lines is very important, because we look at that with the static ropes and cable only systems without elastic in other projects. And when there's such a large variation and potential for high winds and waves, which this location has, it's very important to have an even tension that can be relied on. And as you saw from the layout earlier in the presentation, a lot of these anchors are in very challenging locations. So the scopes of the mooring lines are quite different because the anchors aren't all in one even line around the perimeter. So having different scopes of mooring lines, while it's not a challenge for the elastic system to do it, would be extremely difficult for a static system to handle such a configuration for the anchors and have an even distribution of force. So it's one of the very good innovations that came out of this project to do, which can be applied to other locations. It can be applied with other projects. So it's not a site specific or a design specific type of innovation. So it's very good for the industry.
Yeah, he also asked about if there are any special installation methods needed to ensure the correct even tension in each line. And of course, there are a process in place how to tension these according to the design parameters that we had designed for it. But it's also important to know that it's not so prone to these risks that other systems has been, the static systems that we're referring to, has in the perspective on tensioning and different tensions in line, like Charlie also described here, with these different depths and different scopes and everything. This is possible to do, and this elastic C-flex system is more lenient to this kind of installation versus using static lines. And then I think the last part of this person's question, I think we have replied to that. Okay, another question from a person that actually were involved earlier in this process and hasn't been seeing all the development that has been done in FreShER. But the question is, can the learnings of the project be applied for other locations and projects, or is this approach too specific? And the reply to that is, like I mentioned it earlier, it's very generic for similar projects in the world, and it can definitely be reused and will be reused and is already reused in other projects. So
yes,
that is
basically, Lars, some of the learnings and the groupal work of the partners, as we have explained in the presentation in some slides, give us a methodology to be used that also then after the DNV recommended practice took some ideas about that, and also now DNV is following with this idea with more in-depth approaches. But basically, in my opinion, this project is one of the first times that the sector with the different partners and different goals of each of the partners has met together to assess and think how to build a project, a design, and meet what it will be the expectations of each of these partners in terms of the interest and the safety all together, for sure.
Well, thank you, Miguel. So another question here is how we have been able to exploit the learnings in future projects, a little bit connected to the last question here, if it has resulted in an increased opportunities. And of course, the goal of this system was to lower the costs. As everybody know, there's an extremely important cost perspective on the production of energy and the production cost of the energies coming out of these new type of projects. And there's always a need to press the cost. And the levelized cost of energy perspective that we are having is of course relevant to the how much cost it is per kilowatt hour. It's not only the CapEx we focus on, it's actually the total perspective on things and how much it will affect on the production cost per kilowatt hour. And that is, we even got over that goal, which we're very proud of, and it will be definitely opening up a lot of new opportunities because of this new situation.
Lars, if I may add,
Yes.
just briefly, yes, we will continue having the FreShER website even 1 year after, at least after the project end, where we will also distribute the information. So it will be like a baseline and the reference also for the upcoming initiatives and the project. Besides that, there will be some publications in the scientific papers on the ocean energy and solar energy in particular, where we can sum up some of the findings that could be used as well for the future research projects or similar commercial projects as well. So that could be as well something to keep in mind for the future exploitation of the project's results.
Very good point, Marina. Thank you for that. There is another question that popped in here. How would a square perform, or square orientation, well, a square platform perform compared to this rectangular design? Wouldn't this give a saving on perimeter cost and wave loads? It might do that, I would say, and please chime in from the other participants as well. But it's not only the rectangular design; it's also the orientation of it and how it relates to the bottom depths and the variations, and there are very, very many variables that actually I would say it's more important than the rectangular or square design itself, is my guess.
Yes.
But I
Yes,
think it
but,
would of course affect some way.
Yes, for sure that I agree with the comment of Bastian, but normally we don't install the plant where we want or where the conditions are better. I mean, all the surface of Alqueva we can find. If you have a site in Google Earth, you will have the chance to at first eye to see many places better than this one to install the plant. But at the end, the permits and the footprint of EDP is there, or you install the plant there, or you don't have the plant. So at the end, the FreShER project or all engineering design and all of us will have to struggle ourselves to meet the plant in this footprint, because it's the area with permits to make it. So for sure, it's better to think of the other sides and so on, but it couldn't be the case in this case.
Yeah, exactly. No, so there are other variables that could affect even more, and we could lower the cost even more actually if we had unlimited use of the ground and outside those limits that Miguel is mentioning. The next question is actually also a little bit to you, Miguel. Are the high performance concrete pontoons cost part of the anchor and the mooring line cost? Because they are part of the it is part of the platform cost.
Yes, basically the scheme of this project was that the FreShER project was scoping and facing the costing of the mooring, of the design and the mooring, but all the superstructure, I mean all the floating plant, pontoons and the support, I mean the floats for the panels, were outside the scope of FreShER project and the costing of the budget. Okay, but the different schemes of design that we presented at the beginning, from continuous, discontinuous, different type of tensor belts that we thought at the beginning, were in the idea to reduce the costing of the mooring lines, not only in installation but also in exploitation, because at the end the water depth of this dam is high, is challenging. So for that was the decision to make this type of superstructure of the pontoon around all the perimeter of the plant. Yes.
I think the next two questions
Lars,
here.
Can I add on that for one second?
Yes.
From the FreShER perspective on that, since we were focusing on from the anchor to a final point for the mooring line, the final point from FreShER perspective is the attachment to the primary pontoon, to the larger pontoons. And it was the configuration of the pontoon and the floats is almost a combined configuration. So that's why we, from our perspective here, we have that with Isogenere as part of their solution, because it's also part of an O&M advantage to have those pontoons around there. Also with the connections to the floats themselves, as a lot of people have seen with floats, these types of floats around the world, they usually come with smaller anchor lines, smaller mooring lines, but more of them. So instead of developing a different type of attachment point for this technology, this was a compromise to have both an O&M surrounding and increased attachment point strength, if you say, for mooring lines.
Thank you, Charles. Yeah, I think the two questions here from the same gentleman, I think we can discuss that more in details together directly, because one of the questions if we should meet and discuss this further, which we should definitely do. And one of the question is if we are prepared to share this information in coming disseminations and also in other type of seminars. And I'm sure we should and need to do that and want to do that as well. So Felix, who posed a question here, let's get back to that and set up how we could do that in the best possible way, because we want to share this information, the whole consortium, to everybody in this market, so we can use the outcome and the results that we've been doing here in all the coming future floating projects. I'm trying to read at the same time, that's not so easy. Other topics?
Yeah, more or less the idea. So the questions about Felix, I think that are all related with follow-up situation and how we can evolve or learn about the findings of this project. So I think that, as Lars said, I think that we are open to talk about that, to future initiatives or whatever, for sure.
Mm. And one follow-up question, I don't know about this, it's almost philosophical, perhaps if there were topics that we didn't tackle within the FreShER project. We've done a lot in this project, and it's hard to now try to simulate and then put together a list of what we didn't do. Any comments from anybody else in the consortium about maybe things that we didn't tackle? We've done so good results here, is that what we're focusing on?
I think obviously there are some other options that are still available that we had to pick one design and go with it finally, but there are still different configurations that can be had even within this scope of this design. So yes, for different areas and different locations where there need to be some adaptations, we can definitely use those. So yes, I don't think it's something that we purposely didn't tackle. It's just that there are other options still to go.
Yeah. I mean, I think everybody sees that we have developed a very good tool set, both in the calculations that EDP presented here earlier, all the developments that has been significant from recent years in terms of on the floats and the pontoons and the attachments and everything, and how we also adapted CFlix to these systems. There's now a lot more tools that we can use and want to spread, of course, to others that can be used for future projects. And but every site is site specific. It's something that I learned through my years in the marina industry. And even now, when we look at other projects around the corner, there's of course differences there that where we need to adapt and use these tools in a specific way for those sites. But it is easier now when they are available, and we were showing that how they are practical to use as well. I think maybe there's another, there's how you model that. Okay, there's a question about how we model the hydrodynamic interactions between the floats. This is of course from the industry generic perspective, if we have used it as a single body approach or a multi-body approach, which is a whole new presentation, I guess, on that entity alone. But what do you say, Miguel Vicente from Wayback?
Yeah, thank you for the question. Yeah, we considered a single body. We had this approach. To have the multiple bodies would increase a lot the complexity. There are different ways that we can also try to model the platform motions, the relative motions between different parts of the platform. But we didn't take this approach. We considered the single body, and given the results, it was our understanding that this could be accurate enough to estimate the displacements of the platform and to verify if it would be within the allowed range of displacement. But this could be something to improve in the next project, or at least internally at Wayback.
Yeah. Well, I think now we reached the end. There's no more Q&As or questions in the Q&A here. I don't, or am I missing something? Or Charles, can you see there's
No, there is no more.
There is no more. Okay.
Bye.
So thank you very much to the audience, and also to the consortium members to putting this together, and that we've now had this nice, good webinar where we could tell the world about all our good findings, and hope to see you soon in new projects, in new seminars, and new presentations. Thank you very much for that.
Thank you to all also.
Thank you.
Thank you very much. Thank you. Have a good day.
Thank you. We will close now.